We are once again going to find the flux, that is the surface integral over S of f dot ds. In this case, our vector field f of x, y, z is equal to xi plus yj plus 5k. And S is the boundary of the region enclosed by the cylinder x squared plus z squared equals 1, and the planes y equals 0 and x plus y equals 2. First, let's understand our S. It's the boundary of a region enclosed by a cylinder and two planes. One plane is y equals 0, so a vertical plane, and the other is an angled plane with the trace in the xy plane is x plus y equals 2, that line. I have this drawing here. This is what it is. It's basically like a lipstick. Notice that my x-axis is pointing kind of down and my y-axis is pointing out and my z-axis isn't vertical. And that's the only way that this face of the cylinder, well, the face of the surface made sense to me, right? It's the face that's been sliced by the plane x plus y equals 2. Now, folks, I tried this using a couple of other orientations, and neither one of these looked right to me. And I was looking at this one and I realized, oh, I need to be standing basically here to view this face the way I want to see it. And so that's kind of what told me to put the x-axis down here and the y-axis over here. It's trial and error in trying to understand some of these shapes sometimes. Now, we've got that out of the way. We can see that the boundary, that is the surfaces, constitute a closed surface. And for closed surfaces, we use outward orientation. Let's look at the surfaces that we have. We've got the cylinder. We've got the angled face. And then we've got the vertical face on the back. Let's call these S1, S2, and S3 respectively. The first thing I'd like to do is find a parameterization for each surface. S1 is the cylinder. Remember, it is a cylinder of fixed radius, that radius being 1. Therefore, a good parameterization is x equals cosine of theta, y equals y, and z equals the sine of theta, because remember, it's a cylinder whose trace in the xz plane is a circle of radius 1. We're using theta as the argument of the sine and cosine functions, and then we can use y as the second parameter. Remember, we were limited to 2 parameters. So it wouldn't do to say r cosine of theta and then y and r sine theta. That would be too many variables running around. So it's to our benefit that we have a cylinder of fixed radius. Now, for this cylinder, we do need to think about limits of integration. Theta goes from 0 to 2 pi. Y goes from 0 to the angled face. The angled face has an equation x plus y is equal to 2. So y goes from 0 to 2 minus x. But in terms of this parameterization, we would say that y goes from 0 to 2 minus the cosine of theta. X is equal to the cosine of theta after all. So we'll say that r of theta y is equal to cosine of theta y sine of theta with the limits we just discussed. That one for theta and that one for y. Now let's look at S2. That's the angled face. The face is getting its angle because it's getting sliced by the plane x plus y equals 2. That's a function, and we can write it as y is equal to 2 minus x. I mean, we just did over here a minute ago. When we have a function, our parameterization becomes r of, it's going to be x and z. R of x, z is equal to x, 2 minus x, z. I don't want to use x and y because y depends on x after all. And by using the free variable z, that's how we end up with a vertical plane, right? As far as the limits of integration, let's consider the region D. That's going to be the trace of the angled face in the xz plane. And we can see it's a circle of radius 1, right? It's the base of that cylinder. So we'll say x squared plus z squared is less than or equal to 1. S3 is the vertical face, and it's a circle of radius 1. We were gifted with the equation that y is equal to 0. That's actually y as a function of xz, just like I didn't write it before, but the angled face S2, it's really y as a function of xz. That's also how I knew that r was going to depend on x and z. And for that vertical face, the region D is still x squared plus z squared is less than or equal to 1. Now that we have the parameterizations out of the way, let's consider the normal vectors. I'm going to move some things here. All right, for S1, we know what r of theta y is. So we can find r theta, the partial of r with respect to theta. It's negative sine of theta, 0 cosine of theta. And the partial of r with respect to y is, of course, equal to 0, 1, 0. Crossing r theta with ry is going to give us negative cosine theta, 0, negative sine theta. Let's consider what happens when theta is equal to 0 for really any value of y. If theta is equal to 0, then I guess we would be considering r of 0y, and we're going to get a point that is 1, and then whatever y is, 0. That point on this surface, let's say, is here. 1, whatever y is, 0. At that point, the normal vector that we just computed is negative cosine theta, 0, negative sine theta. At theta equals 0, that gives us negative 1, 0, 0. So at this point that we just identified here, we have a vector that points toward the center. That's an inward pointing vector. That's the wrong normal vector. For closed surfaces, we use an outward orientation. So because that vector is pointing into the center, I know that we actually need the negative, or in other words, we needed our y cross our theta, and that equals cosine theta, 0, sine theta. So if you've found a cross product, just double check that your vector points at the correct direction for pretty much any particular point that you can think of, any point that's convenient, because that'll tell you if you're inward or outwardly oriented. For the angled face, we can find Rx and Rz and cross them together, but folks, we don't have to, because the angled face has the equation of a plane. The plane is x plus y is equal to 2. Recall that the normal vector for the plane ax plus by plus cz equals 0 is ABC, right? That is the direction vector for the plane. Here we have a plane with equation x plus y equals 2. Therefore, Rx cross Rz is equal to the vector 1, 1, 0. And we can see by our diagram that that vector does have an outward pointing orientation. Last, for our normal vectors, the vertical face y equals 0 is in the xz plane, and if we're to have an outward orientation, it needs to point back in the negative y direction. So we're not going to compute a darn thing for that. We're going to say that Rx cross Rz is equal to 0, negative 1, 0, pointing in the negative y direction. Now let's find our surface integrals. I'm again going to move some stuff out of the way. For S1, we have our parameterization. R of theta y is equal to cosine theta y sine theta. We have our cross product, cosine theta, 0, sine theta. So let's put our pieces together. F is equal to x, y, 5. That vector that was given to us in the original problem. we found r of theta y to be cosine theta y sine of theta. So the vector field F with the argument of r, the vector function of theta and y, is equal to x gets replaced by cosine of theta, y gets replaced by y. So F evaluated for r, the parameterization, is cosine of theta y 5. We're going to dot that with the cross product that we found earlier. So the surface integral over S1 of f dot ds is equal to the surface integral over d, we'll get to that in just a minute. The dot product here is going to be cosine squared of theta plus 0 plus 5 times the sine of theta. Using the boundaries that we found already for y and theta, we can see that the integrals are, the first one goes from 0 to 2 pi, and the second one goes from 0 to 2 minus the cosine of theta. We have just used the order of integration dy d theta. I will leave it to you to confirm that this is equal to, if you want to do it yourself before I give you the answer, pause it here now. 3, 2, 1, 2 pi. Now for the angled face. Same f. F of x, y, z is equal to x, y, 5. But we have a different r. So f, the vector field, evaluated at the parameterized vector function r of x, z, is equal to x replaces x. Okay, that's not really a replacement, but whatever. Y is replaced by 2 minus x. And 5 is constant, so it's not going to get replaced like ever. Now we're ready to look at the the surface integral over S2 of f dot ds. And this is going to equal the double integral over the region D, we'll get to that in just a minute, of the dot product of f and rx cross rz. So 1 times x plus 1 times 2 minus x plus 0 times 5. That whole thing is going to be, I'll just say dA, call it the region D. I have my reasons here. So this is going to be the region D, the double integral over the region D. X is subtract out, 2 dA. Now remember what the region D was, folks. The region D was the circle of radius 1 and its interior, so it's really a disk of radius 1. So I'm actually going to erase this D down here. We're going to say x squared plus z squared is less than or equal to 1, because, folks, what we have is twice the area of a circle of radius 1, and so that's going to be 2 pi. I know I kind of weaseled out of that one. If you want to, you can go r d theta and do the whole thing, but I didn't. Now for S3. Same f, right? F of x, y, z, make sure that's a vector f, is equal to x, y, 5. I think I have it memorized by now. But again, a different r. I kind of didn't write down r. So r of xz is going to equal, I mean, really it's x0z. So f of this r of xz is equal to x replaces x, 0 replaces y, nothing replaces 5, so we get x0, 5. All that work, though, check this out, f dot the cross product of rx and rz is going to yield 3 terms of 0. So the surface integral over S3 of f dot ds is equal to the double integral over the region D of, it doesn't matter because it's 0 times dA. That answer is 0. Putting this together, the surface integral over S of f dot ds is equal to the sum of what we just did, right? So the surface integral over S1 of f dot ds, uppercase S, plus the surface integral over S2 of f dot ds plus the surface integral over S3 of f dot ds, our result is going to be 2 pi from the first one, 2 pi from the second one, 0 for the third one. Our answer is 4 pi.